inviting us. Before talking on technical matter, first let me talk on non-technical matter. Last March 11th, there was a very big earthquake and tsunami in Japan. And also nuclear plant accident. I was born in Fukushima, center of the nuclear plant, and grew up in Tohoku area and lived in Tohoku area for more than 60 years. Although I moved to Osaka area far from the Tohoku area before the earthquake, fortunately or unfortunately, I don't know. It was very sad for me to watch on TV that many villages, towns, people, cars, everything were flooded away by tsunami. About 20,000 people were killed or missing by big tsunami. Fortunately, Japan is now steadily recovering from the miserable disaster thanks to the various support from many countries. On the behalf of the Japanese people, I would like to thank all the people who provide us support. Okay, next let me talk on technical matter. The title of my talk is Partitioning Tree with Supply, Demand, and Edge Capacity. This is a joint work with one of my students, Kawabata. I moved to private university, so this one is the first paper written with student in new university. Our motivation came from power delivery problem. All demand vertices can be supplied power so that power flow through edge, namely cable segment, power flow through cable segment should not exceed edge capacity. Such power delivery network is modeled by such a graph. In particular, our graph is tree in which each vertex is either supply or demand, and each vertex is assigned a positive number, 25. This one is a supply of this supply vertex. Supply vertex is always denoted by a red square, and demand vertex is always denoted by such a blue circle, and the positive number is assigned to demand vertex, which means the demand of this vertex. Furthermore, all edge represents a cable segment in the network, and every edge is assigned a positive number called capacity. First problem, called partitioning problem, asks whether this network, particularly tree, can be decomposed into connected component by deleting some edges so that each connected component contains exactly one supply vertex. Every connected component contains exactly one supply vertex, and the supply should be at least the sum of these demands so that this supply can supply powers to all these demand vertices in the same connected component. So 25 is at least 8 plus 2 plus 3. Okay? 20 it must be at least 2 plus 3 plus 7 plus 8 plus 5 plus 1, so that each supply can supply to all these demand vertices in the connected component. We don't allow demand vertex can be supplied power to or more supply vertices. Each demand should receive power only from exactly one supply vertex. Okay? Furthermore, every exactly one supply vertex must be contained in each connected component. The supply is at least the sum of the demand in the component. Furthermore, this one, 14 is a flow value of through this cable segment because 6 plus 8 is 14, and this flow should not exceed the capacity of this edge. The flow through this edge is 8, which is at most the edge capacity. Okay? Namely, capacity constraint must be satisfied. Okay? This problem is, this partitioning problem is yes or no, yes/no problem. This problem asks whether there is such a good partition or not. Okay? And this problem is difficult because it is NP complete for general graph. Even if there is no H capacity, but we can give linear time algorithm for tree even if there is H capacity. Okay. Our algorithm always reduces the size of the tree from bottom to top. Okay. In the following way, we consider any inner vertex whose children are all leaves. Okay. Then one may assume this demand is at least, at most, the H capacity. Leaf demand is at least, at most the H capacity. Because otherwise, this demand cannot be fully supplied power. Okay? So we may assume this demand is at most H capacity 4. This demand 3 is at most H capacity 5. Okay? Then one may assume all these demands are supplied power through the parent. So we can combine these three demand vertices into a single demand vertex in this way, which has demand equal to the sum of these demand, LL. Okay? Then this leaf has enough power to fully supply to this demand vertex, so we may replace these two vertices into a single vertex whose supply is equal to the remaining supply, namely 12 minus 11 is the remaining supply. In this way, we can reduce the size to smaller one. We repeat the similar step to each inner vertex whose children are all leaves. Repeat the same operation to this inner vertex whose children are all leaves. In this way, in this way, in this way, in this way, until there remain exactly one vertex. If the last vertex is supplied, then we output yes, because there is a desired partition. If the last vertex is demand, then we output no, because there is no desired partition. Clearly, this algorithm runs in linear time, linear in number of vertices, However, this yes-no problem quite easy to solve in linear time. However, not all tree has such a desired partition. For example, there is no desired partition for this tree. In such a case, we want to maximize the sum of demand that can be supplied power. Okay? By deleting some of the H's so that the resulting connected component contain at most one supply vertex. This connected component contains exactly one supply vertex. But this connected component has no supply. So these two demand vertices are not supplied power at all. Okay? This connected component contains a supply vertex, so these two demand vertices supply power. Okay? We want to partition the given tree into such a connected component. Furthermore, the capacity constraint must be supplied, okay? Must be satisfied. Then these 1, 2, 3, 4, 5, 6, 7, 8, 9 demand vertices are fully supplied power. The total is 45. So we say this partition has fulfillment 45. And we want to maximize such a fulfillment, namely the sum of demands which are fully supplied power. Okay? There is another partition whose fulfillment is larger than the previous one, which is 49, and this is maximum partition. We want to find such a maximum partition, okay, for given tree. This problem looks quite similar to maximum flow problem, multi-source, multi-sink, ordinary max flow problem, or multi-commodity flow problem. But this problem is actually a generalization of knapsack problem. Actually, this one is a generalization of multiple knapsack problem. There are 1, 2, 3, 4 knapsacks. Size is 17. This size of this knapsack is 20, and so on. We want to tag item to knapsack, one of these 4 knapsacks, but contrary to the ordinary knapsack problem, this item can be packed to this one, this knapsack, only if this item is packed to this knapsack. Okay? Our problem is all or nothing network flow problem. Okay? So generalization of knapsack problem with such a network constraint and flow constraint. Okay? So this problem is NP hard even for trees, ordinary trees. NP hard even for star, in which the root is single, in which the root is only supply. Okay? Ordinary knapsack problem. There is only one knapsack. Okay? There is no constraint in order of item which can be packed in the knapsack. Okay? It's our problem with 4 star graph, which is 3. Okay? So our problem is NP hard even for 3 without H capacity. So we give 2 algorithms First one is exact algorithm for solving the problem for trees, which does not always run in polynomial time, and then we give very good approximations algorithm, FP-TAS. First, let me explain exact algorithm. For every rooted subtree of a given tree, we compute such a DP table, G out versus X. X run over all integers between 0 and F. F is trivial upper bound of the maximum fulfillment. F is minimum of sum of all demands or sum of all supplies. Trivial upper bound of the maximum fulfillment. Okay? We compute such a DP table for all integers between 0 and F. We compute such a graph for each value of X. This value means a maximum flow which can be delivered outside of the subtree through the root of the subtree, so that this subtree has a partition whose fulfillment is at least given value X. We compute such a DP table. Okay? We also compute such a DP table. G in means a minimum flow which must be supplied into the subtree. So the subtree has a partition whose fulfillment is at least a given value X. We also compute 3 more DP tables. First, we compute 5 DP tables for each subtree, smallest subtree, each consisting of single vertex. We compute 5 DP tables for each subtrees. Okay? Then combine 5 DP table for this subtree, 5 DP table for this subtree into 5 DP tables for this larger subtree, and combine 2 sets of DP table for this green subtree and this subtree into a set of DP tables for larger subtree. Repeat the same operation. Okay. Suppose we have already computed 5 DP table for this purple subtree. We have computed such a DP tables. And suppose also we have already computed 5 DP tables for this larger subtree, then combine these 2 sets of DP tables for larger subtrees. There are at most 5 patterns of flow. There are finite number of flow patterns. So we combine these 2 sets of DP tables into a set of DP tables for larger subtrees in this way. Then, suppose we have already computed DP table for the root of the given tree, then we choose 2 of the 5 DP tables. First DP table corresponds to all partitions in which the root is supplied power. Among such partitions, this value, okay, crossing this line, this value is represent a maximum fulfillment among such partitions. And this DP table represent all partitions of the whole given tree in which a root is not supplied power. And this value is maximum fulfillment among these DP tables. Taking the maximum of these two values, we get the maximum fulfillment. Now, each yellow point can be computed in order f time. F is the trivial upper bound of the maximum fulfillment. And there are order f, there are exactly f yellow point, so total time is order f square. Namely, each table update can be done in time order f square, and there are at most 2n table update, so total time is order f square n. If f is bounded by polynomial, this algorithm runs in polynomial time. So then we give f betas. For any small positive error rate epsilon, our approximate algorithm finds solution which is at least 1 minus epsilon times maximum fulfillment. For any small epsilon, and computation time is bounded by polynomial in n is number of vertices, and also reciprocal of the any small error rate epsilon. Idea is very simple. Exact algorithm compute the DP table for all integers, but we use sampling technique. We compute the DP table only for sampled values of x. X equals 0, t, 2 times t, f, and t is a sampling interval. T is chosen to be appropriate value. We compute this DP table only for such a sampled point. Sampling interval is t, and this green line represents a true maximum flow which can be delivered out. Okay? This purple point represents the approximate value. Always our value underestimate true value. Then this value is optimal solution. This one is our approximate solution. So there is an error. There is an error, but the error is bounded by 2 times n because we compute DP table only for sampled value, and the sampling interval is t, so each table update error by t. And there are at most 2n table update, so total time is bounded by 2n t. And so error is bounded by 2n t, t is sampling interval, and we choose t to be this value, so error is bounded by epsilon times maximum demand. One may assume maximum demand is at maximum fulfillment is at least maximum demand. Error is bounded by epsilon times maximum fulfillment. So approximate fulfillment is at least 1 minus epsilon times a. Exact algorithm run in this time complexity because we compute the DP table for all value of x, and there are f number of points, but we compute only for sampled value. The number of points is bounded by f over t, and we choose, f is bounded by m times by maximum demand, and we choose t to be this value. So the number of purple point is bounded by polynomial in n and 1 over epsilon. So computation time is bounded by polynomial in n and 1 over epsilon. Now let me conclude my talk. For tree, we give very efficient linear time algorithms to solve partitioning problem. Yes, no problem. And for maximal version, in which we want to maximize the sum of demand, which can be, which are fully supplied power. We don't allow partially supplied power. Okay? Fully supported or nothing support. No support. Okay? And we give exact algorithm which run in time order f square n. Finally, we give fp task. Okay, the remaining work we should improve this time complexity. Okay, thank you for attention.